Helicopter Flying Handbook 4 Helicopter Components Sections and Systems. Let's unravel the realm of Stability Augmentation Systems or SAS, a technological tapestry woven to enhance the stability of helicopters during flight and hovering, effectively lightening the load on the pilot. These systems come in two flavors: force trim and active augmentation systems. Force trim acts as a passive companion, using a magnetic clutch and springs to maintain the cyclic control in a set position. Picture it as a helpful co-pilot, aiding transitioning airplane pilots accustomed to specific control forces. The pilot can override the system, either by disengaging it through a force trim release button or by applying physical force to the controls. Some recent versions are dubbed attitude retention systems. Active augmentation systems, on the other hand, dive into sophistication, employing electric actuators and hydraulic servos. A computer, finely attuned to external inputs like wind and turbulence, orchestrates three-axis stability. This digital maestro adjusts attitude, power, and aircraft trim for a smoother flight experience. Once activated, the system taps into an array of sensors, from stabilized gyros to electromechanical actuators, swiftly fine-tuning all flight controls without pilot intervention. As with any stability augmentation systems, pilots maintain the authority to override or disconnect these systems at their discretion. Stability augmentation systems, with their intricate interplay of sensors and control inputs, significantly reduce pilot workload. Imagine a scenario where a pilot needs to multitask during sling loading or search and rescue operations. Stability augmentation systems become invaluable. Now, let's shift our focus to the grand conductor of automated flight, the autopilot. A sophisticated cousin of stability augmentation systems, an autopilot doesn't merely stabilize, it takes control, executing functions selected by the pilot. Common features include altitude and heading hold, with advanced systems boasting vertical speed or indicated airspeed or IAS hold modes. The latter maintains a constant rate of climb or descent or indicated airspeed or IAS. Think of autopilots as adept aviators, well-versed in navigation with capabilities like VHF Omni Range Navigation System, Instrument Landing System or ILS, and Global Positioning System GPS intercept and tracking, especially handy in instrument flight rules or IFR conditions. This coupled system can also include a flight director or FD, providing visual guidance cues for selected lateral and vertical modes of operation. Autopilot systems, adorned with electric actuators or servos, connect to various flight controls. The setup depends on the system type: 2-axis, 3-axis, or 4-axis, controlling pitch, roll, yaw, and collective, respectively. The autopilot's central computer, fed by flight instruments and navigation equipment, orchestrates the symphony of control commands. Pilots wield control panels to engage desired functions and navigate the skies effortlessly. Safety is paramount, and autopilots come equipped with automatic disengagement features. In turbulent conditions or extreme flight attitudes, the system gracefully steps aside. Should pilots need a swift override, an autopilot disengagement button, conveniently located on the cyclic or collective, allows for immediate disconnection without releasing control. In this captivating ballet of technology, where each helicopter's autopilot system has its unique nuances, pilots are urged to consult the helicopter's rotorcraft flight manual for specific operating procedures. The journey through the skies, guided by these advanced systems, becomes a harmonious blend of human expertise and digital finesse. Maintaining a comfortable cabin temperature in helicopters involves various methods, each with its advantages and limitations. Ram air, achieved by opening or closing air ducts, provides basic cooling but relies on forward airspeed and outside air temperature. Air conditioning offers more effective cooling but introduces complexity and additional weight compared to ram air systems. A straightforward cooling method involves removing doors to allow air to flow through the cockpit and engine compartments. Proper door storage is crucial to prevent damage and ensure safety. Air conditioners or heat exchangers can be installed, drawing bleed air from the compressor to cool the cabin. However, this system requires engine power for compression, affecting overall engine capability. Piston-powered helicopters use a heat exchanger shroud around the exhaust manifold for cabin heat, while turbine helicopters utilize bleed air for heat, regulated by a pilot-controlled mixing valve. Bleed air, hot and compressed, is mixed with ambient air to provide warmth to the cabin. Preventing the formation of frozen contaminants on helicopter surfaces is crucial for safe operation. Engine anti-ice systems, common in turbine-powered helicopters, use compressed bleed air to prevent ice formation on inlet guide vanes. Pilots control the system using an electrically operated valve. Airframe and rotor anti-icing systems are less common due to their complexity, cost, and weight. Larger helicopters may use bleed air or electrical elements to heat leading edges and prevent ice formation. Research is ongoing for lightweight icephobic materials or coatings to enhance performance. Pitot tubes, susceptible to ice and moisture buildup, are equipped with heating systems that use electrical elements to maintain functionality. De-icing is the process of removing frozen contaminants from helicopter surfaces. Fuselage and rotor blade de-icing before starting is critical, especially for helicopters exposed to frost, snow, or freezing rain. Asymmetrical shedding of ice from blades can lead to component failure, posing dangers to structures and people. Thorough pre-flight checks are essential, ensuring ice removal and confirming free movement of flight controls. In flight, de-icing systems, if available, should be activated upon entering icing conditions.